Hello, y'all. Darrell Berry Jr. here. Bit later than usual. Hopefully, everybody's evening is going well. We're going to continue doing some reading and quantum mechanics, going to chapter 1.5 in Griffiths. So, this section is on momentum. So, we'll take a look at the book as well as look at any concepts or problems that come up along the way. We'll see how that goes. Last time I worked on this problem a bit. So we'll see what problems come up in this one. Momentum for a particle in state psi, the expectation value of x is that. So this goes back to earlier sections when we realized, so let's see if we can deconstruct the foundational understanding from this. Expectation value. So the probability density is psi x of t squared. I'll also put this in discrete format. The expectation value of x is the sum of x times the probability of x. Xi times the probability of xi. And the probability of xi is the number of xi's they are divided by the total number. The weighted amount. So this is the discrete equivalent of this. Exactly what does this mean? It emphatically does not mean that if you measure the position of one particle over and over again, the integral x of psi squared dx is the average of the result you'll get. On the contrary, the first measurement, whose outcome is indeterminate, will collapse a wave function to a spike at the value actually obtained, and the subsequent measurements, if they're performed quickly, will simply repeat the same result. Rather, the expectation value of x is the average of measurements performed on particles, all in the state psi, which means that either you will find some way of returning the particle to its original state after the measurement, or else you have to prepare a whole ensemble of particles, each in the same state psi, and measure the position of all of them. So we have a whole bunch of particles. Looking at this line right here, we have a whole bunch of particles in state psi, and you measure all of these particles and take an average of the measurement. That's the expectation value. So if we have one particle, we have to keep putting that particle back in its original state and then taking a measurement over and over, and that'll end up giving us the expectation value. Or we could have a whole number of particles all in state psi and measure each one and then take the average. So whether we take the average of one particle over and over again after it's returned repeatedly to the original state, or we take measurements of a whole bunch of different particles, all from that original state, and ends up being the same. I like to picture a row of bottles on the shelf, each containing a particle in the state psi relative to the center of the bottle. A graduate student with a ruler is assigned to each bottle, and at a signal, they all measure the position of their respective particles. We then construct a histogram of the results, which should match chi squared, and compute the average, which should agree with the expectation value of x. Of course, since we're using a finite sample, we can't expect perfect agreement, but the more bottles we use, the closer we ought to come. In short, the expectation value is the average of measurements on an ensemble of identically prepared systems, not the average of repeated measurements on one and the same system. So the key seems to be that we're always measuring from the initial state, not measuring a particle, which ends up in a state, whatever state it's in, and then measuring the same particle from its new state. Because if we measure again right away, it'll just give us the same exact measurement we had just now, since the wave function was collapsed. Now, as it goes on, the expectation of value of x will change because of the time dependence of psi. So we might be interested in knowing how fast it moves. But notice that the expectation value does change with time, but the normalization is still 1. So we might be interested in knowing how fast it moves. Referring to equations 1.25 and 1.28, here's 1.28 here. Just remind myself of 1.25. So that's the time derivative of psi squared, which we did last video. We see that this down. We can take a look at all of these. So 1.25. Now it's 1.25. To 8. So if we was to do the partial derivative of t of the expectation value of x, that's partial derivative t of and x would not be affected since it's just x. It should be partial t infinity x. Now I should just plug that in. Partial x Check out the IH bar over 2m, put that in front. Seems right. This is 1.29. This may have been what I was remembering with integration by parts that I had mentioned with my professor. See what we can do here with integration by parts. So if I were to make u be x and du equals 1, and if I also make dv equals the partial with respect to x of psi star psi prime minus psi star prime psi dx. So if I was to integrate this, then I should get psi star and psi prime minus psi star prime psi. And which of my parts would tell me we have h bar over 2m partial with respect to t, and we're taking the partial integration by parts of this, so that'd be x times psi star x minus psi star x psi minus psi star x minus psi star x, and remember the trick that my professor did. So see what the tip is here. We actually did the derivative first. It took the, even though it seems to me that this alternate method should still give the same answer, but take a look at the process they did. I'll just work this x star that equals uh, me turn up sound off. I don't know if y'all heard that beep. Taking the partial derivative of this. Hey, what's going on, BSF? Doing good. How have you been? Thanks for dropping a line. Just trying to refresh myself on this undergraduate uh quantum stuff since I'll be doing the graduate version starting in the fall. So quantum is my weakest subject, as you might be able to tell. So I definitely need some work in it. So I'll try to see if I can get a better handle of this quantum before I enter the graduate class, because then everything will be next level. Even though I spoke with my advisor and a farther progressed graduate student yesterday, and he was saying out of his 4 graduate classes, he quantum was not the hardest for him. So I don't know if it's because he's good at quantum, uh, or the other classes just happen to be harder or what have you. But still, I know that quantum is my weakest, so I'm focusing on it a bit. If you have any questions, let me know. I'll see if I can answer. But I noticed that one of the problems I had was these things like that. If you remember last video, I actually worked out. I forgot to square this one thing here, but I spent some time working on the different sort of algebras that they did. I believe that was just right here. Where we extracted this and did the derivative first before working on the integral. So I think this is another. If you notice, my natural inclination of solving this problem was to just try to do the partial integration, but it seems like the book did this derivative first, like we're seeing on footnote 17. It did the product rule. So I need to remember these tricks to pull out the integrand and actually work it. What's going on, Ujaval? So that looks like a message was retracted. I don't see what it was. Uh, so if I was to write this out, we would have, oh, that's right. I remember now. At least I'm starting to remember. I was saying I couldn't remember the trick that my professor did, but I remember he ended up with uh, the second partial derivative, and this would be why, because he did the partial derivative, he did the derivative first as well. Plus, ah, trying, trying to. apparently this integration by parts should allow this integral to be taken a bit easier. See if we can simplify this somehow. I can't exactly remember. I don't want to, pretty sure I can still access the lecture, but maybe I might have to do that, like go access the lecture of the trick that my professor did. I remember there was something he did here. Hold on. So you do see it right there, because this actually cancels, because this is the partial derivative with respect to uh, psi and psi star. This is partial derivative with respect to psi and psi star. So ironically, that partial derivative ends up with a simplified thing that we're finally taking the integral of. Interesting. So this was this right here. This entire part of the integrand I brought down here and did. So what I can do is just actually copy this down and plug this in and then see what we're looking at. So the idea, I'm trying to get the book answer for this derivative here. So this I plucked out, and I could just plug this in. It is starting to make more sense. And it's starting to vaguely recall what my professor did, because now when I do integration by parts, uh, seems like it'll make more sense. And this x was multiplied by that whole thing. So really I'll have two integrals. If I was to distribute that x to both of them. And I'll just leave it like that for now. So what's the easiest way to do this? Let's go back to the part in the book. This is one of those situations where they just like skipped a bunch of steps, which I think normally they're good about not doing generally. But I guess there's always an exception to every rule, I guess they say. Or maybe I'm actually making this more complicated. Got this tip one more time. The product rule says, so that's what we just did. We just finished doing the product rule. So the product rule simplifies to this. Which follows that the integral from a to b of f dg dx dx equals minus the integral so this one on the right here, if I was to do integration by parts, like you have u, you have du, you have dv, and you have v. So when they did integration by parts, looking at this, the way they have it set up, it's clear that they use dg over dx as dv. So then they just got g, and they used g and f and df over dg. So then they ended up with the fg b to a, even though they put the integral part first, and then the integral of g df over d, oops, to be dx. dx. And BSM says, well, I just want an advice. See, I'm just a high schooler, but I want to pursue physics astro career. Which resources should I refer to for studying? What grade are you in exactly? And it might be a bit of lag. I'll wait for your answer. Looking at this, 11th grade. I mean, it's probably best to stick with uh, your textbooks and things. I'm pretty sure you have a textbook that you're working with. Just stick with your homework. Uh, read your textbook. You know, it's not fun reading textbooks, but I would say read the textbook. That becomes very important as you get into college level stuff. I didn't really read the textbook really until I got into my undergraduate. But I would say it's definitely good advice to start practicing reading those earlier. And I mean, that's pretty much the resources you need right now. As far as help, I do offer tutoring if your parents want to help to just finish helping somebody with their AP physics. He's actually wasn't going into physics. He was, I don't remember what he wants to do as a major, but he just decided to take an advanced physics course. Somebody I was referred to. So I could do tutoring as well if you want more help. But as far as resources, pretty much I would stick with your textbook. Another thing you can use as well, by the way, which is the textbooks I usually utilize when I'm tutoring. Just go to OpenStax, and they have some good physics books as well. OpenStax and physics books. So there you go. But they might be a bit more advanced in what you're doing. Um, so what's the name of your like the physics books that you use in 11th grade? Like what's the author and title of the physics book you're using? I can pull it up and take a look at it real fast. Let's go back to this. So here, oh, I forgot about that partial with respect to t. Gotcha. Yeah. So it'd be good to stay with your textbook so you don't try to get too far ahead. Let me know if you want some help with tutoring. You can talk to your parents. Let's look at this. I think what I'm going to do is I'm going to keep this like this. Do you know the integration by parts method, BSM, for doing integrals? Have you all covered that yet or talked about that yet? Probably not. I don't know. This depends on your school. I do the partial derivative thing. What I'll do is extract this, put this here, and take the time derivative of this. It's a bit ugly. So I'm going to actually apply my advice from before. I'm going to extract this and do this separately. So I'm doing this part right here and see what this simplifies to. So we have partial psi star, partial t. Yeah, I'm gonna have to look at my professor's notes. But I remember there's some kind of trick that I'm forgetting about for this part, but that's why I'm reviewing this stuff. BSM says, as far as the books I don't study in the USA where I'm from, there's a central authority of education from where an integrated sort of book, several different types of books and authors is used. Oh, okay, awesome. Good. What country are you in? Suffice it to say, we're going to end up here, partial x. I may have to, I wonder, should I spend more time studying mathematical methods? Because that seems to be my main issue is the different mathematical methods behind the scenes. But we'll just do a cut here. And I might have to make a video, might review this mathematical method and make that my video next week. This partial derivative, how it works. But suffice it to say that let's fill in steps here. So let me work that out and come and do that next week. Use the fact that d dx equals 1 through with the boundary term on the ground that psi goes to 0. Okay, I forgot about this part. Psi goes to 0 at plus and minus infinity. Do another integration of my parts on this. To get negative I h bar over m integral psi star partial psi over partial x dx. What are we to make of this result? Note that we're talking about the velocity of the expectation value of x, which is not the same as the velocity of the particle. Nothing we have seen so far would enable us to calculate the velocity of a particle. It's not even clear what velocity means in quantum mechanics, but the particle doesn't have a determinate position prior to measurement. Neither does it have a well-defined velocity. All we can reasonably ask for is the probability of getting a particular value. We'll see in Chapter 3 how to construct the probability density for velocity given psi. For the moment, it will suffice to postulate that the expectation value of the velocity is equal to the time derivative of the expectation value of the position. All right. I mean, that makes sense because pretty much that's pretty much all that is. Like we know that dx of dt is v. So, I mean, it makes sense that d average of x dt equals average v. That makes sense. BSM says English isn't my first language, so reading and learning is okay. Understanding all the concepts becomes kind of hard, so I believe tutoring from foreign teachers isn't an option. Makes sense. Makes sense. It's definitely probably easier to learn in your own language. I actually thought about studying overseas before. It is one of the questions that came to mind is learning the language. No, that's the purpose. That's why I'm here. So I'm glad. Thanks for dropping the line. I'm glad you came, BSM. Yeah. So I enjoy interacting with you all. And I may next week work out these steps for these mathematical methods here that are, remember I'll bet this manipulation is going to come up again on some different problems. So look forward to that next week. I'll set that up. And it'll be like mathematical methods of this derivation here. That'll be the plan. Equation 1.31 tells us then how to calculate expectation value of v directly from psi. Actually, it's customary to work with momentum equals mv rather than velocity. Okay, so you just multiply m times that. What I'm doing is multiplying m times this right here. You get the same thing you have minus the inverse m. So interestingly enough, what this means is if we have psi, we can take the complex conjugate of psi. We can take the partial derivative of x of psi. We can multiply it times negative I h bar. And we can integrate it all with respect to x. And then we get the expectation value of the momentum. We also get the mass times the expectation value of the velocity. So that means if we do this and divide by the mass, we should get the expectation value of the velocity. I mean, it makes sense that we should be able to, well, maybe not integrate with respect to t, but if I were to multiply this dt to the other side and integrate with respect to t of the integral, when could we get the expectation value of x? Seems like it. Let me write the expression for expectation value of x and expectation value of t in a more suggestive way. So basically, they broke apart the partial derivative with respect to x. So now we have negative I h bar integral psi partial x psi dx. And since I h bar is just, well, negative I h bar is just a constant, if putting that in the integrand, negative I h bar partial x psi dx, which is the familiar one that I'm used to remembering. We say that the operator x represents position and the operator negative I h bar partial derivative with respect to x represents momentum. To calculate expectation values, we sandwich the appropriate operator between psi star and psi, which is the complex conjugate of psi, and integrate. Right. So basically, we end up with the, I guess, the running definition of the expectation value of momentum. And if we look here, this was the expectation value of x multiplied by the probability density. And as we discussed last week, the probability density is the complex conjugate multiplied by the psi normal. So basically, they just broke those two apart and put the odd factor of x, or I got I bar partial derivative of x in the middle. So these are the main things to remember to get the expectation value of momentum or the expectation value of position in quantum mechanics. What I'll do next week is look at filling these steps for the derivation. So I'll work on that through the week. And next Saturday, that'll be the show. So thank you all for coming up. Thank you all for showing. Thanks BSM for dropping a line. It looks like Ujival was dropping a line as well, but it looks like I don't know if he changed his mind. Uh, but I'll be here next week. I may be here throughout the week as well. But we'll see. But I'll definitely be here next Saturday with filling in the steps for that derivation. And in the fall, I'll be studying the graduate level of quantum, classical, and computational physics, which my understanding is programming, a lot of programming. And I'll also be doing a foundational class, which will be pretty much all of undergraduate physics. So, but I have pretty much a handle on the other parts. Feel like I have a pretty good handle on thermodynamics. Feels like I have a pretty good handle on classical mechanics. So I'll probably still be focusing on quantum as we go through this summer, but I'm sure I'll spice it up and throw in a few of the other subjects as well. So thank y'all for joining. I'll see y'all next week, if not throughout the week. Have a good one.